in the last lecture we had many examples, and through those examples I tried to explain to you the concepts that you have learned in this part of your course. We learned, for example, that the donor energy level is very close to the conduction band and the acceptor energy level is very close to the valence band. We also learned that in the case of carbon, diamond especially, diamond is an insulator, therefore, this difference, this gap, energy gap is of the order of 5.5 electron volts, and in the case of silicon it is only 1.1 electron volt, and for germanium it is 0.7 electron volts. So, we learnt all these things through examples in the last lecture. Now, in this lecture, as I promised, we shall have now two p-n junctions placed side by side, and this whole arrangement is called a transistor. So, or bipolar junction transistor. Bipolar junction transistor, junction because there are two junctions, and transistor, the name I will explain in a moment. So, we will have, having learnt the basics of p and n type semiconductors and the characteristics and the utility of the p-n junction, it is time to think of a device which has two p-n junctions placed side by side or back to back. Of course, these junctions are produced in the same crystal. This I have emphasized again and again. They are part of the same crystal. They have been doped in the same crystal. And the next slide shows the essential structure of the transistor. This is not an accurate diagram, because this is just to show you. Actually, this base P, we have a p type semiconductor sandwiched between n type semiconductors, and this P is called the base, and this base is actually very thin, and emitter, the doping of emitter and collector is also different. Emitter is highly doped to have more electrons, more carriers, and collector is doped only to make it conducting. So, there is a difference in doping and there is difference in thickness, and this base is very thin, and this is, we could have p, n and p also. This is n-p-n transistor, we could have p here, n here and p here. So, we would have p-n-p transistor. The overall structure would be similar, the base would be very thin, and emitter and collector would have different amounts of doping. Emitter is highly doped, collector is slightly doped to make it conducting. So, we can have n-p-n transistor or p-n-p transistor. These are the symbols for the n-p-n transistor and p-n-p transistor. The emitter is shown by an arrow and collector is without an arrow, and base is shown like this. So, this is a symbol of an n-p-n transistor. If the arrow goes inside, then it is a p-n-p transistor, that is, the base is n and these are p and p, emitter and collector are p type semiconductors. Here the base is p and collector and emitter are n type semiconductors. And here are the voltages between the various layers. This VEB is the voltage between the base and emitter. VEB is the voltage between base and emitter, and VCE is the voltage between again base and collector, and VCE is the voltage between emitter and collector. These are the symbols we shall use. The battery in this circuit would be denoted by VCC. In this circuit, the battery will be denoted by VEE or sometimes by VBB, depending upon the connections. So, these are the symbols, and the NPN and PNP transistor symbols are here. The direction of the emitter arrow in the two cases helps recognize the two types. If the arrow is coming out, it is NPN transistor. If the arrow is going in, as in this case, then it is a PNP transistor. The bias voltages are here, various bias voltages are shown here. The working of NPN and PNP transistor is identical, except the polarities of the potentials applied are reversed in the two cases. For example, if we had, this is NPN, if we had PNP, then this polarity would be reversed and this polarity would also be reversed. That is the only change. Otherwise, functioning of both NPN and PNP is almost identical. Only thing is, in PNP case the polarities are reversed with respect to the NPN case. Now, this is how the transistor comes about. We have one junction PN junction here and one PN junction here, and as I have explained in the last lecture, we have a depletion layer, and we have accumulation of charges on both sides. That is, these are the potential barriers. Potential barrier in the NP case is like this. Here in the PN case, it is the opposite. So, these are opposite polarities. So, we have two junctions NP and PN. We have two junctions. They are depletion layers, and this is the base. This P forms the base. This is NPN. This forms the base, and as I have explained, this base is really very thin. And emitter is highly doped, collector is only slightly doped. As I have been saying all along, the continuous diffusion of charges across the junction results in accumulation of charges on the two sides. The charges set up an electric field or a potential barrier. Here are the potential barriers which work against further diffusion. These potential barriers, they disallow further diffusion or discourage further diffusion. When equilibrium is established, there is no net flow of charges across the junction. If it is desired that the charge flows across the junction, the potential barrier or the equivalent battery must be overcome. This is done by forward biasing of the junction. This we have learned. You see, if I want the charges to go from here to here, I must overcome this potential barrier. If I want charges to go from here to here, I must overcome this potential barrier, and these potential barriers are overcome by giving various biases, forward bias or reverse bias. The emitter based junction is always forward biased. I will show you in a moment. The collector based junction is always reverse biased. The emitter is heavily doped. In contrast, the collector is lightly doped, just enough to make it conducting. The purpose of differential doping is to create a large density gradient. You remember that electrons will diffuse to a region where their density is lower than the density here. So, we create a large density gradient by doping them differently. So, that electrons can flow from a higher density to a lower density. So, the purpose of differential doping is to create a large density gradient of electrons to help them diffuse from emitter to the collector. When the emitter based junction is forward biased, the large number of electrons in the emitter are pushed to diffuse across the base into the collector. The name emitter must now be clear. You see, when the emitter is forward biased, it sends lot of electrons to the collector. That is why it is called emitter, as if it is emitting electrons. So, this emitter sends, when it is forward biased, sends large number of electrons to the collector, and therefore, this is known as emitter, and that is why that is known as a collector, because it receives electrons, it is known as collector. So, once again the same figure, we have NPN. I am trying to show this over and again, so that you get to understand what is going on. The base, as I have said already, is kept very thin, so that the electrons stay there for a very short time. You see, electrons which are coming from the emitter will stay in the thin base for a very short time and go away. If it is not a thin one, then electrons would be absorbed or will come in contact with the holes in the base. So, to avoid this, the base is made very thin, electrons just pass through the base and go to the collector. The typical distance travelled by an electron before it combines with a hole is called a recombination length, and the thickness of the base is kept smaller than the recombination length, so that the electron does not recombine with a hole. The probability of recombining with a hole is very small, and the electron just passes on to the collector. A few holes may also be pushed into the emitter and contribute to emitter base current. Obviously, there are various energy levels, particles have various energies, and some have higher energies, they can diffuse on the two sides. So, some holes can diffuse from the base to the emitter, and this gives rise to the emitter base current. So, once again I am showing you this block diagram. This blue line, blue thick line, shows the direction of motion of electrons. Electrons move from emitter through the base to the collector, and then they are circulated around. So, the electrons flow like this. The conventional current, as you know, is in the direction opposite to the direction of electron flow, and therefore, this black line shows you the direction of the conventional current. So, this current, electrons flow like this, current flows like this. So, the emitter base electron flow is like this blue line, and therefore, the current emitter base current is in this direction. Similarly, the current in the base collector circuit is like this. So, this shows the working of a transistor. Electrons coming from the emitter to the collector through the base is made very thin. We can't show it so thin here, but it is made very thin, so that electrons do not combine with the holes and go through to the collector. A few holes, as I have said earlier, can or may diffuse from the base to the emitter, because the density of holes in the base is higher than the density of holes in the emitter. Therefore, a few holes can diffuse to emitter and contribute to the base emitter current. So, that is the working of a transistor. Since the collector base is reversed biased, the depletion layer on the side of the collector becomes wider. Since this is reverse biased, therefore, this depletion layer becomes wider. This is forward biased, therefore, the depletion layer is thinner on this side. So, since the collector base is reverse biased, the depletion layer on the side of the collector becomes wider. The electrons entering the collector are attracted by the favorable barrier potential and are directed towards the collector terminal. This is a favorable potential. The electrons go through this, they are attracted by this potential and go through to the collector. The electrons entering the collector are attracted by the favorable barrier potential and are directed towards the collector terminal, where they are collected and circulated through the outer circuit. That is the reason for this element to be called a collector, because it collects electrons which are sent by the emitter. To collect electrons efficiently, the collector is kept at a much higher potential than the base. Obviously, because if the base potential is higher, then it will attract electrons. So, the base potential is kept lower and the collector potential is kept very high. So, that electrons are all the electrons are collected by the collector. The result is that current flowing out through the collector is much stronger than that in the emitter base circuit. In silicon transistors, the collector emitter current is typically 100 times heavier than the base current. This one is 100 times heavier than this current, because here the potential is kept very high. So, that all electrons which flow from the emitter are collected. In other words, a small current in a signal in the input produces a much larger current in the output. This side is the input. So, emitter base current is very small, but collector base current is very high. So, a small current is magnified many times. In other words, a small current or a signal in the input emitter base circuit produces a much higher current in the output, that is emitter collector circuit. A device which amplifies small signals is called an amplifier, and transistor would work as an amplifier. Here again is the circuit. To clarify matters, we have here NPN, here we have PNP. You can see the polarities here are reversed, otherwise there is no change. Okay. The arrows show the direction of current flow. Here the current flows like this, goes into the collector. Here the current goes out of the collector, and because it is a PNP transistor. How does the name transistor come about? The name transistor is combination of two words, transfer resistor. Trans resistor ka IS, we take ISTOR of the resistor, and transfer TRANS. So, we take this and the word becomes transistor. This name was given to it by its creators. The name was explained in the following words. This is history, you may not worry too much about it, because it is a resistor or semiconductor device which can amplify electrical signals as they are transferred through it from input to output terminals. So, transferred and resistor. So, you can combine these two and this word becomes transistor. That is why this device is called transistor. Now, this is just a summary of what we are going to do. This is not what we have done, but what we are going to do. Depending on the intended use, a bipolar junction transistor can be used in one of the three regions, as we shall see. We can use it in the cutoff region, that there is no current through the transistor, then it is fully off. So, it works as a switch and it is fully off. We can use it in the saturation region, that is when maximum current flows through this, then this is fully on, again it is a switch, but fully on. And in the active region, in between these two extremes, we have a steady current through the collector and the transistor operates as an amplifier. As I have been saying all along, the working of NPN and PNP transistors is completely analogous, except that the polarities of the voltages applied are reversed. The only difference is the response at higher frequencies. Why? Since the current in PNP transistor is caused by the motion of holes, which are a little sluggish in comparison with the electrons, the response of PNP transistors at higher frequencies is poorer than the response of NPN transistors. We saw in the last lecture an example where we found the drift velocities of electrons and holes, we found the electrons move faster. So, holes are a little sluggish, and in the PNP transistor, holes constitute the current, the motion of holes constitutes the current, and therefore, the holes move a little slower, they are sluggish, and therefore, at higher frequencies you can have some problem. Therefore, at higher frequencies the response of PNP is not as good as the response of the NPN transistors. Therefore, for high frequency applications we prefer NPN transistors. Again, to repeat the same thing, this is PNP, you can see from the arrow is going inside. So, this is PNP, and if you compare with the previous figures, you will see the polarities have been reversed here. The current in this case goes out of the collector, in the NPN it goes into the collector, and the current goes out of here and then into here. These two currents are going out, and therefore, IE is equal to IB plus IC if you use Kirchhoff's law. This, if you consider this as a point, then the current entering this are IB, going out are IB and IC, and entering is IE. Therefore, IE must be equal to IB plus IC. Again, we shall do that in detail in the next lecture. These are just the three configurations of a transistor amplifier. The only thing to note is that here the emitter is common to both the circuits. This is known as a common emitter. Here the base is common to both the circuits, input and output. Therefore, this is known as common base, and here the collector is common to both the input and output circuits. This is known as common collector amplifier. We shall see their properties in the next lecture. So, we have common emitter amplifier, common base amplifier, common collector amplifier. These are all NPN. As I have said, there is no difference in the PNP case. The important thing to note here is that this input and this output are out of phase. So, the common emitter amplifier gives an output which is out of phase with the input. In common base and common collector amplifiers, the output is in the same phase as the input. So, here the phase of the input and output is the same, here the output is in a phase opposite to that of the input. So, we shall this has a special function, therefore, we shall this common emitter is actually more often used as an amplifier than these two. These two have their utilities and we shall see what they can do, but most of the time the common emitter amplifier is used as an amplifier. Since these are different circuits, these amplifier circuits, they are different circuits, therefore, they have different properties and different applications depending on those properties. One of the characteristics of the amplifier circuit is shown in the last slide, that is this phase difference which I have already emphasized. the output is out of phase with the input, a phase difference of pi. Here they are in the same phase, here they are in the same phase. So, this is one of the important characteristics of the 3 circuits. And the important thing to remember always is that the base emitter circuit is forward biased. Here in this lecture we studied the structure of the transistor. In the next lecture we shall see the input output characteristics of the transistor and the properties of those characteristics, and then we shall study common base amplifier and common emitter amplifier.